Okay, so in this lecture, we're going to begin our talk about linear algebra, and you'll start with our recap from some of the key lessons learned over the last few lectures involving mean squared error and these loss functions and how we kind of got to this simple linear regression model. And then after that, we'll go through some of the key ideas from Math 18 or Math 20F when I was an undergrad at UCSD, from linear algebra. And we'll probably spend also a good chunk, if not all, of lecture 7 as well, going over these key concepts and reviewing them or refreshing them, as that will allow us to kind of make the bridge to multiple linear regression. And when we work on code and class and stuff, that'll help also make a lot more sense when we're using matrices with these kind of machine learning models that we're writing from scratch. So that will be what we do in this lecture. And remember, you can always ask questions on the online forum, and we'll go ahead and answer them as quickly as possible. It's a good resource, and you should all be using it. Okay, so just to recap what we did in linear regression, remember that the whole point of this was to, given some data set, a scatter plot here with two quantitative variables, home departure time and minutes to school, we wanted to find what the best fit line is, what this line is, and winds up being this equation here for this data set. And remember, of course, that what we're really talking about is this is the best line that minimizes mean squared error. We could have found other best fitting lines. Maybe it could have been that one or this line, perhaps if we were looking at mean absolute error, or of course, if we had a constant model, this could have been the best fitting line. So the best fit line is entirely dependent upon the model that you choose, in this case, simple linear regression. So h of x equals w naught plus w sub 1 times x, as well as also the particular type of loss function that we're using. So just to think about that, we had these idea here that we have a loss function, in this case squared loss, and we're going to use that loss function to determine what the average loss is and minimize it when we have our simple linear regression model. Again, this is our regression model, and this loss function here, which we just plugged the regression model in right there. What we did is we took this and we solved for the partial derivatives with respect to w naught and w sub 1, set both those equal to 0, and solve for the system of equations, which gives us w sub 1 star and w naught star. And this allowed us to determine what that best fit line was, because we have a y-intercept and we have the slope for that line. So that's the key concepts here. We were able to get that, let's use blue, that optimal y-intercept and the optimal slope. And you can kind of, so the optimal y-intercept, that is what it is. It's that's how you write it. But optimal slope, this equation, the idea of optimal slope can be written in multiple ways. We kind of looked at least 4 different ways to write it. This is the traditional way that we looked at, and then we also expressed it as a correlation coefficient right here, and we've also seen it as well in terms of right up here. So the equivalent versions of this would be where we had the sum for x sub I minus x bar times yi over the sum of xi minus x bar squared. And we've also seen it as well in this form as well. So this would be over, and this would be yi minus y bar times x sub I, and this would be x sub I minus x bar squared. So there's a few different ways that we've kind of seen as equivalent ways to look at the optimal slope. So just remember those things. Those are important to know that those all wind up being equivalent ways of describing the optimal slope. And the other thing is this idea that there are many different ways to create kind of this linear-based model. Even though we chose mean squared error, or even though we're using a mean squared error, and mean squared error might use the same symbols like W naught star, W sub 1 star. They're going to yield different parameters for W naught or W1, whether that's a value or it's zero. In the case of the constant model, the y-intercept has a value, but in this case for simple linear regression, we have two good values. But in the case of the constant model, we just have one value, the mean for W naught, but W1, there is no slope for W sub 1. That's non-existent. And in the model where the line goes through the origin, there is no y-intercept. That's zero. And we just have a slope that we use. And that slope kind of just sort of pivots the line. You can kind of think of it as, where your slope might look like that, or like this, or like this. It's all around the origin. So these are just different ways of trying to determine, using mean squared error, optimal parameters. And those parameters, what we have to use are W naught and W1. So it's that's the kind of concept that we've been thinking about here, is why are more complex models or different models appropriate? And those are largely dependent upon the data set. If you have a data set, so for example, like here are two data sets, and we have something like this, and then we have something like that. In the case for the right-hand model, having something that passes through the origin may make a lot of sense. Whereas if you have a model like this, having a line pass through the origin would not make a lot of sense. So for example, if you're trying to predict housing prices, it is not the case that a house's price is $0, as much as I would like that. It doesn't exist. So having the y-intercept pass through the origin is not going to be a very good model for that particular data set or predictive task that you have, because the real world data generating process doesn't have houses that cost $0. Whereas if you do have something where your dependent variable does have a value of $0 at some point, then that very well could make sense to have a model that passes through the origin. And realistically, even if you were to use mean squared error with the traditional way we've been doing it, it would most likely still minimize down to where the line did pass through the origin or very close to it. So if your data truly did go through the origin. Okay, and I suppose also just to round out the constant model, just we all have it. That's where we have something like this, and the dependent variable is that y-intercept. So okay. So this is what we've kind of been doing, and it's important to note that when you have a better understanding of this stuff, the reason why we're going through this stuff at such depth is so that we see how the mean squared error, based on the model you're using and your data set, changes, and how it relates to things like the mean absolute error. This kind of stuff can really help you to make good modeling decisions. And I know this is not advanced machine learning or neural networks or deep learning, even though the simplest neural network you can create is linear regression technically. Understanding machine learning and these data science concepts from these theoretical fundamental levels shows you, the pathway to learning more advanced stuff and doing it in a rigorous manner. For example, this regression line we have here, obviously this is where we have some model where it's a W naught plus W1x, and we have our constant model, which is just going to be the y-intercept essentially. So, what can we say about these two things? Well, one thing we can say is that if we take the mean squared error of both the regression model, simple linear regression model, and the mean squared error of the constant model, we're guaranteed that the mean squared error of our regression model will always be equal or less than, this is the mean squared error now, so the function that we're minimizing, the mean squared error of our constant model. So yeah, this is because at the very optimal way of doing it, if this data set was just a straight line that didn't have any slope to it, then the optimal prediction would just be a horizontal line. But the second that a data point shifts up or down, the optimal line must move with it a little bit to reduce that error. And so that's why the MSE, I mean, in a plain way to phrase it, that's why the MSE for the regression model will always be less than the MSE for a constant model. Yeah, so these are things that we're doing. Remember also too that the MSE of the constant model just winds up being the variance of the data set. That's another thing that we covered, and that these things always pass through X bar, Y bar at some point. Okay, so let's go ahead and begin by sort of going over some of the basics, the fundamental stuff from linear regression that you should remember. If it's been a while since you've taken linear regression, this will be a good refresher. And if you do remember quite a bit from it, it'll be good to see the buildup of it and the parts that are particularly of importance for these kind of like fundamental stuff that we're going to be looking at. And yeah, I think this will be a good refresher for everyone. Okay, so we'll start by looking at dot products, and we're going to spend a lot of time on dot products and trying to have a really firm understanding of these basic concepts. As we go and have a much more complex regression model that we're creating, we really lose the ability to start to visualize these concepts on a plot, especially once you get past multiple parameters. So you have your W naught, but then when you have your W1, 2, 3, so on and so forth, or sometimes they're called beta coefficients in multiple regression. Once you have too many of these parameters that you can no longer put them on a 2 or 3-dimensional graph, even on a 3-dimensional graph, it becomes very difficult to understand conceptually what's going on unless you have a firm grasp of how the stuff works using matrices and vectors and spans and projections. And from previous DSC40A classes, we've seen that there's kind of a big drop off in retention from what you learn in linear algebra, and so that's kind of why we want to go over this, because this is calculus is important, but certainly for machine learning, and certainly with working with more advanced models and anything with deep learning like linear regression or linear algebra is one of the most, if probably not the most important mathematical subjects that you'll learn. So it's good to have a good foundation in that. If you haven't watched it yet, either do it now or you can do it later after this lecture if you've already watched it. But 3 Blue 1 Brown has some really great videos that visualize some of these things, and it's hard for us to do these visualizations in this kind of lecture format. But hopefully this lecture, coupled with the things we do in class and coupled with those kind of like nice online intuitive videos, we're really trying to build like the intuition behind some of these core ideas and concepts. It's a really good thing to do. So I recommend watching that as soon as possible, and you can watch it 2 times speed. I'm sure you're probably watching my lectures at at least 1.2 or higher time speed, because I try and talk very slow through the math stuff just in case people want to take it very slow. But yeah, please watch this. This is a good idea. And full disclosure, obviously linear algebra is an entire quarter, which should be a semester long, like a 16-week long class, to really digest a lot of the ideas. We're not going to be able to cover all those ideas, nor are all those ideas explicitly required for this class or doing machine learning. But you all have taken linear algebra before, so there might be some stuff, I'll try and minimize this as much as possible, but there might be some things that you will be required to do or know that we don't have time to explicitly cover, or there'll be some logical leaps occasionally. So just watch out for those, and I'll try and remember to discuss or tell you about them as I do it. But yeah, these would be a good thing for you to keep in mind. Okay, let's go ahead and we'll start by looking at vectors. Okay, so we start our discussion in linear algebra with vectors. Of course, you remember a vector in R being the real numbers, R of n, and is the number of real numbers in our vector, and it's just an ordered collection of n numbers. So let's take this explicit. R is the real numbers, and n in this case, are the number of n real numbers. In our vector. Okay, and vectors commonly are written with a lowercase letter with an arrow on top, and almost always write vectors as columns of numbers because they are an ordered collection of n numbers, and the order of this matters a lot. But sometimes we'll write them, especially if there's a space, like a reason for space constraints, as kind of like an array or a list. But you always have this t here, this transpose, because when you transpose a vector, you kind of take it and you turn it 90 degrees essentially, and that's what happens when you transpose a matrix. You go from a column to a row. And if you think about, like, maybe if you've taken a physics class, this idea of a vector is some sort of object with which is typically like an arrow that has a direction and a magnitude. So it would be like 6 kilometers going north. That would be like a vector. And in our case, the reason why order is important here is because you can kind of think of these vectors as kind of instructions on how to get somewhere. So this is kind of the idea to think about here. And another way we can describe a vector is that it has, in this case, v has 4 components. And we say that v is in R4. So this little symbol here that you'll see is, this is called technically set theoretic notation. But what it really means is, it really means the word in, or it could be an element or member of the set. So we'd say here v is a vector in the vector space R4, or is a member of R4. So this is just kind of a refresher for vectors. Pretty easy so far. I guess also one other quick one is, instead of the R has 4 components, we could also say that R has 4 elements. It's also another way you might hear it being described. Okay, so this would technically be element of or member of, just to kind of round out this definition. Okay, so all right, so we have this idea of a vector now. What does that actually mean? Well, we see here this vector. Vectors always start at the origin, and they go in some sort of direction. They point to some sort of, a vector points to some point in space. And the direction of a vector is of extreme importance. And when we describe these vectors, we would say, in this case, for this vector right here, maybe I'll start to write some of this out, that this vector v is of the form 5, 3. So we'd say v equals 5, 3. We know it's 5, 3 because we go 5 and 3, and that gets us to this neighborhood, this location in the in this space. And a vector can be defined by its length. This is called the L2 norm. And this here should be somewhat familiar. It looks a lot like the Pythagorean theorem, and this is really just the multi-dimensional Pythagorean theorem. That's the sum of the squared components of a vector is its length. So that'd be a good thing to write. This is the let's write it all out. Sometimes I have this habit of using 2m, so I'm trying to do a shorthand for dimension. The multi-dimensional Pythagorean theorem. Okay, and we'll use this theorem over here to actually calculate the length of this vector. And Well, maybe we'll just do that actually right now. Okay, so let's go ahead and do that before we get into direction or magnitude. So if we wanted to find out the length of this vector, and we know the vector goes to 5, 3, so we could just use the multidimensional Pythagorean theorem equation here, and we could say, let's see, it's equal to, and we have the square root, and this is v21 plus v22 plus yada yada yada. In this case, we have 2, we have 5 and 3, so this will be 5 squared plus 3 squared. And that's it. And that equals 5 squared plus 3 squared will give us 34. Okay, so that's the length of this vector. So what does this 34 actually mean? Well, it means that from the origin, the point to where this vector goes to, 5, 3, is 34 length. Now 34 what? 34 units. Arbitrary, but it's 34 unit, or square root of 34 units from the origin to 5, 3. And that's nice to have. We know the length of it. And now if we want to know where this vector points to in space, we can bring up some probably almost certainly forgotten all of this, but we can bring up our high school-ish level trigonometry. So we're going to have some sort of, I'll use purple this time. We have a theta in here, and that's the angle. And we know we have 0, 0 at the origin, just to make this clear for all you, 5, 3. Okay, and so what do we have here? We actually have a triangle. So we know that this is 5, and this is 3. So what we really have is 5, 3, theta. And how do we find theta? And this is, of course, a right angle. We use the tan inverse. So we would say theta equals tan inverse of 3 over 5. And this, I mean, full disclosure, this, whatever this number winds up being, whatever theta winds up being is whatever. It's not important. I mean, we can find it out. But it's this idea, that we want to keep in mind that we can find the direction where this vector points to. Okay, so that's the angle of the vector. And moving on, we come to the dot product. And the dot product is probably the most important concept from linear algebra to really have a firm grasp of. It's not that the dot product is inherently difficult, it's that it needs to kind of become almost second nature, especially when we start thinking about doing multi-dimensional calculations, especially when you get to like things like deep learning, where you have kernels that you're multiplying across input matrices, things like that. Like this idea of multiplying vectors becomes very, very important. So what is the purpose of the dot product here? And in a nutshell, the main purpose of the dot product is ultimately to tell us how close together two vectors are, or how well aligned they are. How well are these two vectors aligned versus like these two, and they kind of going into the same direction. This is an important part of it, and the output of a vector or of a dot product of two vectors is always going to be one number, and that number is a scalar. So in this case, we have, maybe we should just draw these out using the color. So we have, we go with purple, we have the vector u, which is at 2, 4. So we could say that u is equal to 2, 4. And we have the vector v, which again is equal to 5, 3. And a dot product can be written as, so this is the vector v dot product with the vector u dot product of vector v, and you'll see this written both ways. So this is taking we transpose u and multiply it by v, and the reason why we do that is because the inner dimensions of the two vectors being multiplied need to match. So we'll show that down below. But the strict computational definition of it is I suppose Oh yeah, okay. Let's just write it out, and that'll be more clear before we go into the transpose version of it. Okay, so let's use these same colors. So in this case, we have U times, well, I guess I also have to use black too now, times V. And that's going to give us 2 times 5. So U sub I times V sub I. So that's, yeah, we're going element-wise and multiplying these elements this way. So we're going to have 2 times 5 plus 4 times 3. So we're going to have 2 times 5 plus 4. So 2 times 5, and this will be 3. And then here we'll have these, which is just going to equal 10 plus 12, which will give us 22. And this is our scalar. Now, if you want to write that transposed in the transpose format, which is a common way to think about this, this would be vector U transposed. We don't need the dot anymore. And this will be V, which is going to equal our transpose vector of 2, 4, which again, we just kind of like, rotate it. So we have 2, 4, and 5, 3. And that is, again, going to equal 22. But the important thing to see here, I'll do this in yellow, is that we have a, well, I'll do actually in purple. We have now a 1 by 2 dot product to a 2 by 1, because the first number in this is the number of rows and the second number is the number of columns. And when we're multiplying vectors, the 2 inner dimensions need to match. Doesn't matter about the other dimensions, but the 2 inner dimensions need to match. So this is going to be our very brief introduction to dot products, and maybe to make sure that we're all on the same page, we'll go ahead and we'll do a quick question, and then we'll go back and kind of, so we've taken this coordinate definition now. We've looked at the coordinate space for these dot products, and then we'll look at kind of like a geometric interpretation of the dot product, which we'll use we'll try and learn. We'll try and see a little more about what's happening with the angle between these two vectors. Because remember, at the beginning, I said that one of the main purposes is to tell us how close together, how well aligned two vectors are, and the closer together two vectors are, this theta value, the angle between them, changes. So this is the brief introduction to it. We'll do a quick question and then go into more of a geometric interpretation of it. Okay, so which of these following expressions is another expression for the length of vector v? So pause the video maybe and take a moment to try and think about it. I'll give you a hint. It's not E. Okay, so let's think here for a second. We have these like v squared things, these v vector squared things right here. So what's going on with these? Well, there's no real linear algebra operation for squaring a vector like that. We could say that vector v squared is an undefined operation. Obviously, there are in like some of Python or computational libraries like perhaps Pandas or NumPy, which Pandas is built on. They have operations that allow you to square everything, all the elements of a vector, and do things like that. But by itself, this is not something that is really a defined operation. So you can say B and D are out. So and the reason why is, let's just try and do it. Let's pretend like we have some vector v, which equals, right? So this is a 1 by n, we have one column and n rows. Well, what would that look like? We would have v times v. And so in this case, we would have a, oh, no, no. This is n by 1, sorry. So in this case, the number of rows we have, in this case, would be n by 1. So this would be a n by 1 times an n by 1. And we know that 1 does not equal n here, so we don't know what to do. If this was just a 1 by 1, then of course you could do it because it's just 1 by 1. You're just multiplying two numbers. But in this case, we don't have that. This is a generalized expression for the length of the vector v. Okay, so that leaves us with A and C, which are both potentially viable, but we'll soon see. Let's go wait for purple. So let's assume we have v times v here. So what would that look like? That would be, if we did this multiplied across, we would have something like so we have v, the first element of v1 multiplied by with itself plus the next element in v multiplied with itself for all elements in v multiplied for itself. And this looks awfully close to, the definition that we had earlier. Right? This looks awfully close. What's the only thing that we're missing? Well, what we're missing is square root, which then equals the magnitude, or sorry, the length, the L2 norm of the vector. So this would be the correct answer. And I want you to also think, this is like a good, maybe good little hint to give. When else in linear regression have we taken the square root of summed square components, right? Like we've seen this before. We've done stuff like this in simple linear regression. And so this is where the connection, you can kind of start to maybe see things and how they're lining up. We've done things like this when we did our simple linear regression. So there's a thread here that we want to think about as we're going through this stuff. Okay, let's move on to the geometric definition, and then we'll do another example problem. Okay, so for the geometric definition of the dot product, what we're really interested in finding out is the angle between these two vectors, and that will tell us a lot about their direction and how similar they are to each other. Because when we get into orthogonality in a few slides, we're really going to want to make use of the dot product and try and find vectors that are 90 degrees to each other. So with the geometric definition of the dot product, the vector u dot product with the vector v is equivalent to the length of both of these individual vectors times cosine. Cosine being the angle between vector u and vector v. So for this, let's go back to, let's kind of draw this out again. So we have 2, 4 for vector u, and I suppose v. And then for vector v, we have 5 and 3 again. And let me write that a little better. We want to try and find where theta is here. We know that's going to be equal to the inverse cosine of something. So we got to figure out what that is. And we can write this now that we know u and v. So we could say u, and we'll do it again down there. Okay. So the whole point of this is we want to kind of equate the computational and geometric definition of the dot product so that we can solve for cosine, because we're going to get this, and we're going to get we're going to get this, and we're going to get this, and we want to solve for cosine. So what does that look like? Well, the dot product of the vectors u and v, going back to our computational definition, is going to be same as last slide: 2 times 5 plus 4 times 3, which gives us 22. And then for the geometric definition, we are going to take the length of vector u and vector v times cosine. And this is going to be v and u. And that's going to give us, let's see, square root of 2 squared plus 4 squared. And that's going to be the square root of 5 squared plus 3 squared cosine, which will give us 4 squared plus 2 squared, 20. Write that a little better. That would be 5 squared plus 3 squared, 34 cosine theta. That's that answer, and maybe we can highlight this is what we want and this is what we want, and we will take these two things and we're going to want to equate them. We can do that in green. And we will do that. Let's just do that up here. Yeah, it's okay. So to do that, we're going to have 20 and 34. So we'll have 20, 34 cosine theta equals 22. Okay, so we'll just get the cosine by itself, and that will give us, let's see, cosine of 22 over 20 square root 20 square root of 34. Now let me just rewrite all this. And we can simplify this. Let's see, square root of 20 be square root of 4 times 5. Pull the 4 out, give us 2. So square root of 20, square root of, square root of 4 times 5, which would give us 2, 2, 5. So we could turn this into, let's say it would be 22 over 2, 5, 34. This becomes 11, the 2 goes away, and maybe just, nope. So that'll be the work for that, and then that will just give us cosine theta equals 11 over, let's see, 5 times 34, 170. 170. And so that will turn into 11. Let me write this a little bit better. That will turn into cosine, inverse cosine of 11 over square root of 170. Again, we don't really care that angle is necessarily in this case. That's just, because I know calculator figure that out. But that's the operation. How we use the geometric definition and the computational definition for the dot product, set them equal to each other, solve for the cosine, and that gets us the angle between the two. So let's go ahead and you pause the video and try doing it again on your own. This is a slightly more difficult one, but still the same operation. Okay, let's go ahead and begin this one. So again, we have the vector u and the vector v. So we can say the vector of u is equal to, in this case, 4, 1. So 4, 1, and we have the vector v, which is equal to -2, -4. And then we can just use the computational definition and the geometric definition. So the computational definition will just be u dot product v, which is also going to be u transpose v, or vector u transpose times vector v, which would be, in this case, we'll take u and transpose it. So 4, 1 times -2, -4, and that will give us, let's do it right here, 4 times -2 plus 1 times -4. I guess I'll just write it out. 4 times -2 plus 1 times -4, which equals -12. Write that a little bit better. -12. So that's one answer. And then we take the geometric definition, where that will again be the vector u dot product the vector v, which is the lengths of u, v, cosine, and that will just give us, let's see, 4 squared plus 1 squared, and that would be -2 squared plus -4 squared cosine theta. Ooh, I had in mind. And that would just give us, let's see, 4 squared plus 1, 17. -2 squared, 1 plus -4 squared, 20 cosine theta. And that's our answer. Okay, so we have these two things, and now we're going to go ahead and plug them in. So we'll do that up there. So this will be 17, 20 cosine theta equals -12. Isolate cosine, and we can do that with cosine theta equals -12 over square root of 17 square root of 20, and we can break apart the 20 into 2 times the square root of 5 again, and then we can remove the 2 so that -12 becomes a -6. So it'd be -6 over the square root of 17 times the square root of 5. And we have cosine now equals -6 over 17 times 5, which is 35 plus 50, so it's square root of 85. And now we know that theta down here is equal to inverse cosine of -6 over square root of 85. All right, so that is our final answer for that. All right, so again, not a particularly difficult operation to do, just have to remember the steps and what these things have in common. And what we really want to get out of this is we want to be able to understand when we have these angles between these vectors and they wind being like perpendicular and right angles. When two vectors at the origin are orthogonal to each other, that means that they're perpendicular or they form a right angle. And that's when the cosine of 90 degrees is 0 between the two vectors. So this is probably one of the most important, another one of the most important concepts, because orthogonality is an idea that's used quite a bit in machine learning, as it allows us to find nice transformations to do. So again, we had our v vector, and then we had some sort of u vector, and this is the origin. And when there's 90 degrees between them, we say that they are orthogonal. I suppose when you say cosine 90 degrees, orthogonal, whether perpendicular or there's a right angle. So this is what we mean. The dot product between them is 0, and when we have this, there's the key idea here is that if and only if. So what this particular thing is saying is that if and only if statement. Which implies bidirectionality. So two vectors are said to be orthogonal if and only if the dot product between those two vectors is 0. So this is an important concept. And of course, I guess it also presupposes that you don't just have a vector of zeros like the 0 vector, because then the 0 vector, which is just 0 by itself, is orthogonal to all other vectors in that space. But beyond that, this is the key idea here. And one quick thing that we can do, just as a refresher, find a non-zero vector in three-dimensional space, which is orthogonal to the vector 2, 5, -8. And there are, of course, infinite possibilities for this, because we're really just trying to solve for solutions to 1 plus 5, 2, 3 equals 0. So finding the vectors that we can multiply these three values and equate to 0, which are infinite possibilities, will give us vectors that are orthogonal to the vector v. So for example, a really quick one could be, so probably one of the simplest ones is just to set one of these equal to 0. So we would have 0 for one of them, and then just you invert 5 and 8. So since one of these is negative, we'd say 8 and 5. So by getting 0, we get rid of the 2. So the 2 is gone, and then we have a negative here. So we just need to multiply the 5 by an 8 and the 8 by a 5, and they'll cancel each other out to equal 0. So in this case, this would be 0 times 2 plus 8 times 5 plus 5 times -8, which of course is just 40 plus -40, which is equal to 0. Another simple example. Another example could be, let's see, we've got 8, so let's just do let's do when we're not setting it equal to 0. So let's get 8 times -8 would be 64. So we'll put 8 down here. And then something times 2 plus something times 5 has to equal 64. So 5 times 11, no, that'd be 55. 5 times 12 is 60. So 12 here. And then 2 times 2 is 4. So I'd give us 6. So I'd go 64. So then this would just be 2 times 2 plus 12 times 5, 64 minus 8 times -8, 64 equals 0. So we would say that the two vectors 0, 8, 5, so whatever we just call this, let's just call this vector x and vector y. Vector x and vector y are both orthogonal to 2, 5, 2, 5, 8, 2, 5, -8 to vector v over there. Okay, so that's the idea behind orthogonality. So next we'll go over spans and projections, and we'll be on the way to wrapping up this this lecture. We'll up some of the things we'll begin talking about, but this is a good sort of intro to some of the basic concepts. Okay, so now let's look at spans and projections. Remember when we're adding and scaling vectors that we want to take, for example, this vector v here and add u to it. So we go from the origin to v, and then we take u and add it on, and that gives us this sort of like parallelogram. So here we have v, and this is over 1 up 2, so this would be over 1 and up 1, 2, about right there. So then this would be like that. This is u. Or we can also take v and go the other direction, which would be like that. And this creates a sort of like a parallelogram here, which has this diagonal in there. And that diagonal is u plus v, or v plus u. These are element-wise operations. So when we sum vector u and vector v in nth dimensional space, then that's how we arrive at this. And we say here that the outcome of vector u plus vector v is another vector. So this right here equals a vector, where when we were multiplying two vectors before, we were just getting a scalar. Now then, this is the case where we're adding them. If we were to multiply a vector by a scalar, so in this case c is a scalar, we multiply a vector, let's say for example we multiplied u. So here we have vector u is equal to 1, 2, so that'd be 2, 4. Let's say that we multiplied it by -2. Oops. So -2 times vector of u, which would be -4, -8. And when you multiply a vector with a scalar, for example, if we have this going this way, if you multiply it, you just wind up going further in the direction. So this is multiplied by a positive, and then if you multiply it by a negative, it just goes in the opposite direction. This is the origin. So in this case, if we have u, we multiplied it by a negative scalar, which would be -2, this would go in the opposite direction because it's negative, and then we multiplied it by 2, so it's going to go not just to right here, which would have been -2, -4, but it's going to go to -4, -8. So right here. So it'd be -4, -8, because this is -2, 2 times u. So -2, we're just flipping it around and then going double the distance. Okay, so linear combinations. In this case, we have this new thing here, d. And I want to make it clear that d is just a catch-all for vectors, like the number of vectors we have. So when we say let v1, v2, all the way to d, we're talking about the number of vectors. So we have here d vectors, and since we have n, we have n components or elements in each vector. So v1 can be anything, it could be whatever vector we want. For example, we could have vector v1 equals 2, 3, and vector v2 could equal -1 and 4, and v3 could equal 0 and 9. These are all valid possibilities. They're all v vectors that span R2. They all have 2 components to them. And by saying that we have a linear combination of these vectors, we can say for each of these vectors, we can multiply them by any scalar. So for example, we could have, in this case, we could have 2 v1 plus just v2 plus, I don't know, 1/9 v3, and that would equal some mystery vector, but that vector is guaranteed to be some vector in R2. Right, and this applies for anything. We could have 0, v1 plus v2 plus, or we can go like minus 2 v3, and again, we're always going to get some mystery in R2. So what we say here is that a linear combination of any set of vectors is a vector that you can make by scalar multiplying or adding a vector. And that's just a really kind of simple definition of what linear combinations are. It's important to be in that R space though. So that's what we say for for linear combinations. And if we're looking at spans, what we're looking at, and there's actually in that 3 blue, 1 brown video, a really nice kind of visual interpretation of, or visual intuition that is built for the span of a vector space. I suppose you could say that the span of a set of vectors is the set of all other vectors that can be reached by using whatever component vectors as building blocks. So for example, we have some space here, and we have 2 vectors. We have, and let's say, doesn't really matter. The only caveat is that the 2 vectors, one of them can't just be a vector stuck at the origin, and the other one can't be a vector that overlaps it or goes in the same direction. The exact where the angle between them would be 0. That you can't have. But even if there's just slightly off, so this is not okay. But if we had something that was just even ever so slightly off, that would be okay. And the reason why is that, think back to that parallelogram. Using, for example, these 2 vectors or any number of vectors, we can combine these vectors, use them as kind of like Lego building blocks to reach any other space in R2. So we can use these two vectors. Like if I wanted to get to over here, I could just take this vector and scale it, and then take this vector and add it. So we can kind of move these vectors around to get to here or here. Like for example, if we wanted to get to over here, we could just so let's say we wanted to do a little more of a convincing one. Let's say we wanted to get to this point. How would we do it? Well, we could take v1 and go and multiply it by like -2, the scalar, and then we could just add that so this is just v2, so that would be this would be -2 v1 plus v2 equals our mystery point. So we can get to that point by using linear combinations, so the scalar and addition of the vectors in this vector space, to get to any point, and that could be any point anywhere, anywhere in here. We're just using these linear combinations to get to that point somehow. So we took v1, multiplied it by 2 going backwards, -2, and then we just added v2 to get to that point. As long as these vectors, again, are not overlapping, they're just off by a little bit, going in any direction, as long as they don't overlap. In R2, we can get to any of these points. Even if it's just ever so slightly off, we can still scale and manipulate them to get to that point. So let's, I guess real quick too, this is maybe just to finish it off. In this case, we would say we have v1 and v2, so we could formally we could say v1 and v2 span all of R2. Okay, so let's go through this exercise. We've got these 3 vectors, and we want to know if vector y, so 9, 1, is in the span of v1 and v2. So logically we can say yes, because v1 and v2 aren't scalar multiples of each other, right? Like they point in different directions. So that's important, right? So v1 and v2 are not scalar multiples of each other, I suppose. So, they like in this example, they point in different directions. They're not scalar multiples. There's a slight deviation between them. So what would we do? We'll write y, the vector y as a linear combination of v1 and v2. And since this lecture is already taking up enough time, there's one more thing I want to talk about. I won't actually solve it, but let's set the problem. Let's see, v1, v vector, into vector 2, and that equals 9, 1, and we get this, from this idea here, to see if it spans. And if we wanted to set this up, we'd have, let's say we have 2 and -3, so we'd have 2 and -3. That's vector plus, we've got -1 and 4, so that's -1, 2, and 4, W2, and that will equal 9, 1, and then we would set this up to solve like 2 W1 minus W2 equals 9, and then -3 W1 plus 4 W2 equals 1, and then we would solve for W1 and U2, and at that point we're just talking about algebra, so that's how you find how that spanning for 9, 1 works. But let's go ahead and finish talking about how let's get a little bit into this idea of projection. That's one of the last things I want to talk about in this lecture before we wrap it up. Okay, so let's wrap up by diving a little bit into, or dipping our toes into, this idea of projection. And this is really important because we're taking the basic concepts of linear algebra, and now we're trying to see how we can relate two different vectors to each other. And this ties into the idea of minimization of some error. And you'll see that in these next two slides. So here we have two vectors, x and y, and you'll also note that we're starting to use x and y because it's similar to what we're doing in machine learning, where we have some x's and we're trying to predict a y, and variables that we're used to. But anyways, x and y are two vectors in two-dimensional space. And the span of x is a set of all vectors of the form wx. So w is a scalar that scales x, and it's the set of all scalings of x that we could have. So for the vector x, there's a w that gives us this. There's also one that gives us double that. There's one that gives us negative, right? And really, there's infinite number of them because we can scale x positively or negatively any amount that we want. So what we have here is kind of like a number line, and we can scale x however we want. And we want to know, for this vector x, what is the scalar that, well, I suppose maybe a better way to say it is, of all the possible spans of x, which one is the one that most closely resembles y? Now you might be saying, okay, well, x is just a straight, is this vector right here, and y is the vector going the other direction. So there's really nothing like it. And intuitively that's true, because they're both going in different directions. But what we can say is that this is not like y at all compared to this, right? At least like this is going in the same direction as y, kind of, compared to this. And we can also say that this vector here is not as similar as y compared to like this vector, right? Like this has some sort of length, and this right here, we'll call this like x1, and we'll call this one like x2. Like x1 is more close to y than x2 is. And what we really want to find is some projection that minimizes, or that makes these two things as similar as possible. Okay, so this is the idea of a projection error. So intuitively, if we just think of x as some sort of line, and this is just being a point, then how do we calculate the error? Like thinking back to linear regression. Well, we would just take this point, and then we would just drop a straight line down right here, and this would be that that error. Like, or linear regression, this would be like a residual. So what is this line when it's minimized? Right? This line is a smaller error than that line, or than this line, or that line. Intuitively, when this error line here, E, is orthogonal to x, we would say that E is the minimum distance, right? It's the smallest E could be, right? Any other E here is larger than the E that's orthogonal to x. So we want to find, let me just draw it now. We want to find this E, this other vector. Because if we know that, then we know what this wx is. So wherever the vector E is orthogonal to x, wherever that point that it drops, we then know what scalar to use w on x, the vector x, to get to that point. And the idea here is we want to make E as short as possible, and that occurs where w, the vector x, is orthogonal to us. And this entire idea is very reminiscent to the idea of minimization that we've been dealing with. And this sets us up nicely because we can do these kind of calculations in n-dimensional space. So this is what we will spend the bulk of next lecture kind of exploring, is this idea of minimizing projection error in n-dimensional space, and trying to really understand how we can use these building blocks of linear algebra to solve these kind of minimization problems in higher dimensional space where we have many x's. Okay, so that's all for this lecture, and we'll see you in the next one.